Hey, welcome back. Today we're going to be talking through what a dot product is and how to solve dot product problems for physics and AP Physics classes, specifically in the context of work. What do we mean by work, and how do we use a dot product to multiply two vectors together and get a scalar answer in the form of joules? So I'm going to show you what we're talking about, but first I do want to talk about what we previously talked about in terms of work, what we've previously learned, and I've talked about how work is equal to the force parallel to the motion times the displacement through which that force is applied. So check this out. What we want is the component of this force that is parallel to the D. So it's almost like if you imagine a triangle right here, we want this component of this force that is in the same direction as the displacement we have. To be able to get that, we would say force times the cosine of theta times the displacement is going to give us our work. And I've talked about that previously in a previous screencast. I'm going to put a link to that in the upper right about now. But today what we're doing is building on that idea for AP Physics classes. And so this is going to be a general dot product method, and this is going to be used for work, but other things besides work as well. So you can use this in other scenarios. And on your equation sheet in AP Physics C, you're going to see this, and it basically means the exact same thing as what we have over here. It's just stated a little more generally, and it's got a couple things that you have to be careful with it, but it's really not a big deal. If you have two vectors and you have the angle between them, what we can do is take the magnitude of one, multiply it with the magnitude of the second vector, and multiply it by the cosine of the angle between them, and then what we end up with is the same thing that we have over here. So this is a more general concept with different nomenclature, meaning a different writing system or labeling system here. And so this is A dot B. So the dot product of vectors A and B would be equal to this, A times B times the cosine of theta. Now I want to be careful, in here, implied in here, we're talking about the magnitudes of these two vectors right here. So I've modified the AP equation down here for clarity, and I want to point that out. Something else I want to point out is that there are a couple different ways of calculating the dot product. I'm going over the way that you're going to see on your equation sheet and the way that I think is really intuitive, and I'm going to compare those two. There are a couple other methods that you can use as well, but these are the two most important for your understanding and for your day-to-day operations of how to solve problems. Alright, so let's see how this works out in terms of an example problem and compare the two. So take a look at this example problem right here. If you have a force of 2.1 newtons and a displacement of 2.3 meters. Now notice real quick, this almost looks like a free body diagram, but be careful, it's not a true free body diagram because we are mixing vectors here. We've got a force vector here and a displacement vector here. So it's not a true free body diagram actually. But the way we would calculate this is we would solve for the component of this force that is parallel to the motion. And so that would be F cosine theta times the displacement through which that force is applied. So we go through and do the operation here. We end up with 3.8 joules. That is a scalar answer, by the way. Now let's see what would happen if we did this with this method over here, the more generalized method that you have on your equation sheet, on the back of your equation sheet. So we would say A dot B is equal to vector A times vector B, and the magnitude of both of those times the cosine of the angle between them. And so notice we are still going to get 3.8 joules. And so essentially, either way you want to think about it, you can do these problems in the context of work. Now, in a more generalized context, this is going to be more helpful because this will apply to more things than just work. But it is important to note that if you can understand this, which you probably can, this will help you to understand what we mean when we talk about this over here. Alright, and let's talk about directions. So let's talk about directions and signs for our answer. So if we have two vectors like this, and let's say this is our origin and this is going to be the positive x-axis, one way to talk about direction is to think about this positive x-axis right here as being the 0-degree mark, and then as you go counterclockwise back from that, you go around 360 degrees, ending up at 0 again. So like for instance, this would be 90 degrees as measured from that positive x-axis. This would be 180 degrees as measured from that positive x-axis, and so on. Alright, that's just another way of labeling angles. Well, if we label our angles that way, we can say, for instance, that if you have an acute angle where in your first quadrant right here, you're going to end up with positive work being done, and it works out using cosine that it works out that that is the case as well. If you think about it, this is your first vector multiplied by your second vector times the cosine of some number that's in between 0 and 90 degrees. Well, if you do that operation, like if you take the cosine of some number in between 0 and 90 degrees, you end up with a positive result. And graphically, this is what is happening here. We're interested in right about here is where that first vector, it's parallel. F parallel right here ends up, and we're multiplying it by the second vector over here to get the dot product. Alright, so if we take a look at this scenario right here, where the angle is going to be over 90 degrees but under 180 degrees, what do you think? Are we going to end up with positive or negative or zero work being done? Well, we're going to end up with negative work being done, and you can test this out. You can try taking the cosine of a number that is greater than 90 but less than 180. Assuming you're in a degree mode on a calculator, you're going to get a negative answer. And how about this scenario over here? What do you think? Are we going to end up with positive work being done or negative work being done? Alright, well in this case you can see that we're going to have negative work being done. The component of this force right here that is in the same plane as the second vector over here is in the opposite direction. So because of that, it's going to be a negative vector in terms of graphically what's going on, but also in terms of the math if you plug in a number between 180 and 270. Alright, the last one over here, if we're going to end up in our fourth quadrant down here, we end up with positive work or a positive answer when the cosine of a number is going to be greater than 270 but less than 360. So that's how to deal with dot products in a physics or an AP physics class. I'm going to build on this though, and there's more to say about work because I want to talk about work that happens when you have a varying force, a force that is not constant. How do we calculate work in that regard? Because that's more like real life as well. Forces are not always constant in real life. Hopefully that's been helpful. I'm going over all of the concepts for a year of physics as well as a year of AP physics. And so if you have any comments down below, please let me know, and I hope you all have a great day. Take care.